Okay, let's take a look at this parameterization of a curve. We have right here linear dependence of x on t and y on t. T is the parameter which will run between 0 and 3. So first we need a picture of how this thing is behaving just with x depending on t and y depending on t. So I'm going to quickly graph a couple of pictures for each of these curves right here. This, therefore, is the t-axis being the independent variable, and my x being dependent on the t is my dependent variable, so I put it there. And I'm going to be looking at graphing this line 2 plus 3t, which is, of course, a line with a positive slope and passes through the x-axis somewhere here. Okay, so graph that line there. Scale isn't important here. We all know what lines look like. This thing is going from t equals 0 to t equals 3. So I really only care about this portion of the line, in fact, and what's going on in between that point and that point. So because of this inequality right here, technically speaking, these portions of the line are not present. Okay, and they should not be included in our drawing. Let's see, the coordinate pair here for our initial x value. So remember, at the starting t parameter value, we call that the initial point. So we have an initial x value right here. If I plug in t equals 0 here, I obviously get out x equals 2. So the coordinate pair for this thing is 0, 2. And the coordinate pair for this thing at the terminal point, when the parameter is equal to 3, would be 2 plus 3 times 3. So that would be 11. So we have over here 3, 11. Okay, that's what our x coordinate's doing. It's a steady increase from the value of x equals 2 to the value of x equals 11. Okay, next, let's take a look at what the y coordinate is doing. Now, the y coordinate is a little bit steeper. It's a 6t, and it is a line passing through the origin. So let's go ahead and graph something that can represent a line through the origin. Once again, we're only concerned about t values going from here to here. Oh, sorry, I should label that t and that y there. And your output point right here and input point right here. Once again, I'm not actually graphing anything that's to the left or right of there because of this inequality. It says that that part of the graph is not present. Okay, it's not in the domain of this function after all. Now, these coordinate pairs as well, let's go ahead and get those. So plugging in the initial parameter value of 0 here gives me a y0. So obviously that's 0, 0. And this guy right here, plugging in that 3 right there. T is equal to 3, y is equal to 3 times 6, so 18 there. Okay, now let's go ahead and think about what this now looks like on the xy plane. Okay, so t can be thought of as a variable for time. The parameter is time, and as time passes, the point on our xy plane changes its position. From what we have right here, we have a good amount to be able to get the final picture of this thing. So this is my standard XY plane. We know, for instance, that the initial point is going to be at the coordinate pair of 2, 0. My initial point is for t equal to 0, and so I get x equal to 2 there, and y equal to 0 there. So my initial point then is 2, 0 on this graph. Okay, so let's go ahead and maybe put an x coordinate of 2 there, and we're plotting it at y equals 0. So we've got that point right there. Okay, that's my initial point. Now for my terminal point, the t value is equal to 3 at the other end of the range of the parameters, and plugging in that t value into my formula for x. You can see we did it right there. We got 11. Plugging in the formula for y, we get out y is equal to 18. So our terminal point is equal to our 11, 18. And so we're going to need something over here, 11, and something way up here, 18. Okay, and we've got this terminal point right there. So let's go ahead and label these. Our terminal point, 11, 18, and our initial point, which is, of course, 2, 0. Okay, now the question that's left is, how does our curve get from this point to this point? Okay, is it taking a strange wandering path to get from this initial point to this terminal point? Or is the pen perhaps moving in a linear fashion, moving from this point to this point? Well, we can already see, for instance, that the x-coordinate has to be constantly increasing, and the y-coordinate has to be constantly increasing as time passes, right? So whatever this is doing, I can't, for instance, have my x increasing and then turn around and go backwards, because that would make my y and my x decreasing. And I also can't turn around and go backwards this way, because it would make my y decreasing, okay? So that's, a lot of point in favor for this actually being a line. How can we actually find that line? Well, you might guess it's the line joining these 2 points right here. How can we tell for sure? Well, this is where our main lesson for this example comes in. When we are able to solve for the parameter, then we can actually put our equations together into the form of a more familiar x versus y equation. Okay, and that equation will be good enough for representing the curve as well, but only when we can solve for that that parameter that way. Okay, now for my x coordinate right here, let's just describe what I'm going to do right here. So let's solve for t, and combine the x and y equations using substitution. And what you'll see is that we are able to eliminate the parameter, we call it. Let's actually enable that right here. Eliminate t, elimination of the parameter. So I'm going to solve for t right here in my x equation, say, or my y equation. In this case, it looks like solving for it in my y equation is actually a little bit easier. So I'll go ahead and do that. Let's say y over 6 is equal to t. And now I can substitute that in to this equation right here. So I have 2 plus 3 times y over 6. Okay, that's what we did with that substitution there. And well, that's definitely an equation for a line, because both x and y are first powers there. Okay, so for instance, you could, if you wanted to graph it, put it in a more familiar form, I suppose. This is a y over 2 and x right there. So we could move the 2 over there, y over 2 here, multiply both sides by 2, and we have 4x, 2x minus 4, excuse me. 2x minus 4 is equal to my y. And let's see, for that equation, plugging in my initial x value right here, just to check my work right here. If I plug in x equals 2 in this equation, I get 4 minus 4, which is 0, and my y coordinate there is indeed 0. If I plug in x equals 11 here, I'm hoping to get out 18. 2 times 11 is 22. 22 minus 4 is indeed 18. Okay, so we have now justified that this thing is a line. Technically speaking, the line that I have graphed right here is actually, let's underline it in green right here, would actually be the whole line off to plus or minus infinity. Okay. Now, obviously, that's not what we have here because we have an initial point and a terminal point. Just like up here, there are certain parts of this graph that should not be present. And so this equation describing our curve is actually not sufficient. Okay. We can see, for instance, that the x parameter, the x coordinate can only go from 2 to 11. So this is actually only good for x between 2 and 11. And now when I include that, I can finally say that what I'm actually getting is just the portion between here and here. Okay, so I'm going to go ahead and maybe double line this like that so I can distinguish these two. Okay, so that's just going from 2 to 11 right there. So this is a portion of our answer right here. This is an equation for our curve just in terms of x's and y's. We've eliminated the parameter. And the final thing that I need you to do whenever you are asked to graph one of these parametric curves is express on your graph the direction that we're traveling. So remember, what our parameterization is doing is describing the movement of my pen along the plane. So did I move from here to here in a straight fashion, or did I move from here and then sort of jog backwards, like scribble my way up to the terminal point? You know, there are actually a lot of ways that your parameterization can trace out the exact same line. Okay, so you need to describe exactly how that gets done by including arrows. Okay, so this will be pretty much everything that I have on the page right here is required information in your work.